the internet started to come into something, we knew it would change our lives. And then again, in about late 2000, 2010, when iPhone became a thing and App Store became a thing, that also changed the way we live. And now in early 2020 to mid 20s, AI became a sort of thing, and it's going to change our lives in a lot of ways. And today, I'm quite happy to have this guest lecturer today, Dr. Joshua Chang. He's one of my old friends and also probably one of the smartest people I've known. So he will be sharing with us on the artificial intelligence in medicine. Round of applause.
Hello, very much for having me, Tom. It's a privilege to be here, and I'm glad to be able to share with you a little bit about the stuff that I've been working on and share with you my story as well. So my background originally, I was in electrical engineering and computer science. I did my master's work in missile defense. Was very interested in signal processing and artificial intelligence. This was about almost 20 years ago now. Seeing people, it was really interesting to kind of come up with new algorithms and new tools, but defending ourselves from missiles was not as interesting for me. And I wanted to be more applicable in terms of how do I help people for real. And so after working for a couple of years, I went to medical school and I got my medical degree as well as a research degree. And how do I take all of the tools that I understand and learned in signal analysis and computer theory and artificial intelligence and apply it into medicine. And so that's what I get the chance to be able to talk to you about today, and I'm really excited about this possibility. So as we get started, I just want to know a little bit more about you, actually. And so this first slide that I have here, this is just an interaction that you guys can go ahead and use the QR code. You can start putting in answers if you want. Basically, where have you used AI? And so hopefully as people are able to log in and are able to put stuff together, we'll start seeing it pop up on the screen. Revision, okay. And you can, if you see a word that you've used as well, you can use that same word again. It'll just make the word bigger. So we'll see kind of which words are there you go. So revision, more people are using it for school and for revision. Vibe coding. I like that, whoever put that down. ChatGPT, yeah. Okay, so you guys have used kind of a very broad range of different things, school being kind of the biggest thing probably, which makes sense. Horoscope, that's interesting. I haven't seen that one before. Statistical analysis, writing personal statements, yeah. So this is awesome. So I mean, I see how you're using it. Just out of curiosity, if you were to raise your hand, how many of you have used AI? So most of you have used AI. That's great. So what I want to do today is talk a little bit about how AI works, give you a little bit of intuition as to how do we understand AI, and then ultimately take you then from there and see how we can apply a lot of that logic and a lot of those thoughts to medicine specifically. And along the way, I'll share with you some examples of how I've used AI in my own. So let me. So as John said, this is the age of artificial intelligence, right? We see AI in almost every aspect of our lives now. These are just a couple of the examples I'm going to put up here. But how many of you use email, for instance? Everyone's using email, right? How many of you have a spam filter on your email? Probably everyone as well, right? Now, spam filters are a form of AI, right? It's learning over time what is something that you're interested in versus what is just kind of junk mail. Any of you watch Netflix, YouTube, some kind of streaming service of any sort? Some of you. The rest of you are very good students that are not watching. So like whenever you get these recommendations afterwards, right? After you've watched the show or watched the video clip, it'll tell you, hey, this is what I'm going to recommend to you, knowing, thinking that you might also enjoy this as well. That's also an AI algorithm that's kind of putting that there, right? And so these AI systems have been around for a long time. These aren't that new. They've been there for years. Any of you like to go shopping online? You know, Amazon, Lazada, Shopee, all of those also will have recommendation systems. And a lot of, again, those recommendation systems they're learning what it is that you like to buy, and then it's recommending to you other stuff that you might also like to buy as well. So one of the big things I want you to think about when we're talking about AI is a lot of it comes down to what are my inputs, what am I learning from, and what am I kind of recommending or suggesting or outputting from our model here. You know, we've got systems like, for instance, iRobot, at least, I don't know if it's as popular here, but, you know, we have automatic vacuuming machines now on the floor. In Austin, where I'm from, we recently have driverless taxis now that are starting to show up on the streets. And I heard Bangkok is also having some of those as well, but a lot of those are, again, also AI as driven as well. And so one of the things that I want to start off with is whenever we're talking about terminology and things is how do we understand this and what exactly is it? How do we make it work? So there's really kind of four goals that I'm going to be touching on. So I'm going to focus a lot more on the first two, and I've talked with Gan about like potentially we might have a couple of others video series or lecture series later that will cover the rest of this. But I want to first define what it is that we mean by AI or machine learning or supervised machine learning. A lot of these terms that are being thrown around, I want to first explain what it is first and give you some intuition on how it works. And then the second thing is, how do we use it? And one of the things that I want to propose to you today is that I think for a lot of the work that's done done in a hospital or in the healthcare setting, a lot of it should be spearheaded by people like you all. It should be spearheaded by doctors and not by engineers. And I think I can say that being an engineer, that we really shouldn't be the ones leading the project. It really should be first coming from the doctors to give first a framing of the problem, an understanding of what the problem is, and then kind of helping to monitor the entire way through. Now, oftentimes what happens is doctors see AI, and then because they don't know anything about AI, they're very hesitant to get involved. And so they'll say, well, we'll just leave it to the engineers to deal with it. And what I propose is that oftentimes what happens is when we do that, engineers will misinterpret or misunderstand or think about some things differently because they don't have the same experiences a lot of you may have in the hospital setting, in the clinical setting. So one thing I have learned by working in this intersection is language, we're all using the same words perhaps, but the meaning is very different between what a clinician says and what an engineer hears, and also what an engineer says and what a clinician hears. And so, but hopefully by giving you some of this language, by giving you some of these tools and understandings, you will be able to communicate a lot of this better and understand what the engineers are saying in order to build better AI systems for healthcare. All right, so first off, let's define what are these terms. And so what is artificial intelligence? This is just a dictionary definition, the capability of computer systems or algorithms to imitate intelligent human behavior. It is a very broad definition that says as long as the computer can pretend to think, that's considered artificial intelligence. And so let me show you what is a really simplistic way of thinking about this. How many of you have ever played the game tic-tac-toe? All right. So tic-tac-toe, you have a frame, you know, a 3x3 grid. You put X's down, you put O's, and then your opponent puts the O's down, and then you kind of try to get 3 in a row in tic-tac-toe. Now, all of you probably in your brain have a set of ideas of what is the best move you should make, right? And so we can actually program into the computer system, if I see the board looking like this and I am the first person to move, then always put an X in the middle. That should be your first move. And so I can program a computer to, if it sees a tic-tac-toe board, it'll put an X in the middle. And then if it sees this kind of board right here with O on one side, it's going to then put an X in the corner, and so on and so forth. We can build a huge library of if-then statements, essentially, covering every single possibility. And then so that way the computer will know if I see this state of the tic-tac-toe, if I see this positioning of all the characters and where everyone is, I know what the next best move is, right? And so this is a very basic form of artificial intelligence. It's called a rule-based artificial intelligence system, where all it is understanding if I see this, then I do that. All right. And actually, this is probably developed back in the 70s, the 60s. This is not a new idea. And one of the early applications of this was actually in medicine. So how do we take this rule-based artificial intelligence and apply it to medicine? And so this was a, whoops, sorry. This was a, so this was the paper that was published in 1970. A group out of Stanford University actually developed this system. And what they did was they developed 600 rules to diagnose and treat bacterial infection in a patient. And so they would ask questions of the patient or of the clinician that's treating the patient. You know, what are some of the observations? What are some of the symptoms that are arising? What are some of their allergies? How old is this patient? And feed all of that information into this big rule-based system. And then it would output, you should give this patient, you know, this particular antibiotic or this particular treatment. And so this was a very complex rule-based system, 600 rules at the time, in order to achieve this. And it worked extremely well. Now, the problem with this was in 1970s, computers were not as prevalent as they are today. So the amount of computing power it was needed to have one of these things running was huge. Not every hospital, not every clinic could have one of these. At that time in 1970s, a lot of doctors were hesitant of the AI taking over jobs. They thought, what happens if the AI system gets it wrong? Who's to blame? Is it the doctor using the computer system? Does the computer system get sued? What exactly happens? So there were legal issues. There were ethical issues with regards to, do we really outsource life or death issues to a computer? There were technological issues. And so because of all of that, back in 1970s, this didn't take off. It was just kind of a really interesting intellectual exercise, but no one applied it, no one used it. In many ways, we're at a very similar point today in our world right now, right? There's a lot of AI systems that are also being used. I heard a talk recently that at least in America, there's probably 100 or so different AI systems that have been approved by the FDA and are available for us to use. There's an actual billing code for a lot of these things now. And of all of those systems, maybe only 4 are used at any moment in time. It's a very rare thing for a physician to want to build an AI system. And so, again, understanding why that is the case and how do we think about this is one of those things that was a problem back then and is, again, still an issue that we have to wrestle with today. So this is the entire space of artificial intelligence. And what I'm going to do is I'm going to start breaking down some of these other terms. And so the next term I want to talk about is machine learning. And you may have seen in the literature, a lot of people will say AI/ML. A lot of people might use AI and machine learning interchangeably. And what I want to do is at least just give you a technical definition of the difference between these two things. And so machine learning here, again, I'm going to just pull up the dictionary here. The process by which a computer is able to improve its own performance by continuously incorporating new data into an existing statistical model. What this means is you take that rule-based system that we talked about previously, but now imagine that I showed you something that you've never seen before. The rule-based system wouldn't know how to handle that. It doesn't have it in its memory banks. It doesn't know, what do I do with this new state? And so machine learning is this idea that it can take new information, reincorporate it into its system, and update its internal model, whatever that may be, whether it's statistics, whether it's a computer model, whatever it is, it's updating, and it's literally learning over time. So the more information you feed it, theoretically, machine learning algorithms versus the broader AI algorithm, machine learning algorithms specifically will be able to take that new information and get better over time with it. So let me, again, just put it in the context of as students, many of us, I know at least for me, when I was going into medical training, I don't know if board exams are as prevalent here, but when I was studying for my first board exam, we have these books that just give you all of these pieces of information, right? Something like 13,000, 14,000 bits of information. If you memorize all of this stuff, you should be able to do well on the board exams, right? Do you guys have something similar here? No. Yes. Yes. Okay. I see some nods. So when you take any kind of these board exams, shelf exams, as medical students, I know for myself, a lot of it was how do I memorize all of this information so that when I see a question, I can immediately remember that piece of information, apply it, and then answer that question, right? It's very much which of these rules have I memorized and how do I apply it into here? Now, on the machine learning side, you might have a doctor here, a master physician or a clinician who has not just memorized all these rules, but he's seen a lot of patients, right? And many of you, this is what the purpose of residency is, the purpose of internship, fellowship, and just your lifelong education as a doctor is you're seeing more and more patients over time. And every patient you see doesn't always fit perfectly into one of the rules. But by seeing that patient, you are expanding your rule-based model in your head, and you are now thinking, oh, wait, I haven't seen this before, but it looks very similar to this other patient I've seen before. It has very similar features to this other person. We did this and it worked. We did that, it did not work. And so now you are, in many ways, you are a learning system, right? And humans are learning systems. We're not rule-based. We use some rules to kind of kickstart our education, our learning. But after that, the thing that makes us different than just a simple rule-based computer is that we are constantly updating that information. And machine learning is trying to mimic that in what it's doing. All right. So let me give you an example of how does, let me show you this first. There's going to be a whole bunch of terms that, there's a whole bunch of terms here that you may or may not have heard of. And what I'm not going to go through all of these today. I'm going to focus on just a couple of them. But you may have heard support vector machines, random forest deep learning, LLMs. If you have used ChatGPT or anything similar to that, that's an LLM. What I want to do is, I don't want to so much get bogged down in a lot of this terminology just yet. I want you to understand how an AI system works first. And then a lot of these things are tools that will help you implement a lot of that. All right. So I know that John Gunn and I have talked about like potentially doing a couple more lectures, and maybe in those lectures we'll go into some of the technical details here. But again, this first lecture, all I want to do is just give you a very big picture of how does it all work? How do you gain some intuition about it? And how do you start thinking critically about AI systems that you read or you hear about in the news or you read research papers on? How do you start thinking about that? So what I'm going to do specifically is I'm going to talk about supervised machine learning here. And let me just give you an example of what that is. So this is going to be a game that we'll play. You guys can think about it in your heads, but I've got two categories here. All right. And what I'm going to do is I'm going to tell you, I like all of the objects in the green box, and I don't like the objects in the red box. And I want you to try to guess what the rule is. Try to see if you can learn what is it that I like and what is it that I don't like. All right. So if all I've given you is these two data points, I like cats and I don't like owls, all of you are probably already starting to formulate some hypotheses in your head, some ideas in your head, right? Anyone want to shout out one possible thing that's what do I like and what do I not like? Pigeons. All right, so how many of you think I like pigeons? And how many of you think I don't like pigeons? All right, so many of you think I don't like pigeons. And why do you think I don't like pigeons? It's a bird. So right now you've formed an initial hypothesis, right? You've extracted some information. So you're not reading cat as a three-letter word necessarily. You're looking at it, you're thinking about it, and you're thinking it's an animal. Same thing with an owl. And so you're thinking maybe it's whether he just doesn't like birds. So let me add a little bit more data here. So let's say I've seen a cheetah and I've seen an osprey. And an osprey, not to ruin it too much, but osprey is another bird. But let's say I just give you some more and more data. So we've got oriole, which is a bird, and ostrich, which is a bird, cougars, and lions. And so now all of this information is in some ways confirming for you that picture in your mind of what is it I like and what is it I don't like, right? And in many ways, in the hospital setting, we do the same thing, right? When we look at a patient, when you're looking at the data that's coming in from a certain patient, you're saying, well, maybe their heart rate is elevated, maybe their white blood cell counts are elevated, maybe they're starting to body temperature starting to go up, and then you're starting to think, well, all of the signs of sepsis, for instance, are starting to click in, and then you're now thinking this is probably a picture of sepsis. So again, like you're generating these. You're looking at some of the feature, the data that's coming in, you're making some extrapolations from that, and then you're making a classification in many ways. Is this patient septic or non-septic? Now, what happens though if I suddenly give you, let's give you a few more. So still now you might still be thinking I don't like birds, but now I've got ocelot and alligator. So ocelot is like a cougar or a wildcat. So now I've broken the rule, right? Whatever hypothesis you have had now is no longer valid. Now, how many of you still have an idea of what is it that I don't like and what is it that I like? Now, as you're thinking about that, most of you are probably thinking through, well, what is it about all of these animals on the right and what is it about these animals on the left that are different, right? You're starting to create, again, more and more hypotheses. You're looking at which aspect of these words, of these animals, should I be focusing on? Does anyone? Yes. I don't like vowels. Good job. So that's exactly what it is. So I don't like animals that begin with vowels. And everything else is okay. All right, so if it begins with an A, E, I, O, or U, I don't like them. Now, what I want to show you through this exercise is though that each of these words, there's a whole set of features associated with them, right? You can look at these words as, how many letters are in the words? What is the animal represented by those letters? Does it start with a vowel? Does it start with a consonant? All of those things. Those are all elements of what that word is. And in many ways, just like when we see a patient come in or when we see a blood sample come in or a histological slide come in, there are many features associated with each of those items that come in, right? And so if we want to say, well, here are all the patients, and so let me show you this slide here. This is what's known as classification. And I have a study that we're doing now, right now, where we're looking at a lot of these infants that are born preterm or early in the hospital. What's been surprising to me is, I think, at least in the United States, about 10% of all infants are born before 37 weeks or are considered preterm. And as you all are probably aware, if they're born preterm, that means a lot of their systems are not fully developed before they're coming out a little bit early. Some of them are really early. Like we have some patients that are coming out 24 weeks, 25 weeks, so super early. Their neurology is not fully developed. They're not breathing well. And so one of the things that we've asked ourselves and the clinicians have talked to us about is, well, how do we identify which patients are at higher risk of becoming septic, for instance? I have all of these patients, and again, each patient has a whole lot of information associated with it, right? What's the right feature for us to look at? Just like many of you guys, when you're looking at the words earlier, you're trying to come up with a hypothesis of, well, what is it that differentiates these patients from these, or from these words from these other words here? And you're generating a whole list of ideas based off of the features you're kind of dissecting from those words. And in many ways, what AI is doing is the same thing. It's taking these patients and whatever data you feed it, it's trying to identify, well, what features are differentiating this population from that population. Now, this is important because if I were to just feed in, I want patient A, patient B, patient C is in this group, patient C, D, and E are in this group, and nothing else. I don't feed in any, history and patient, medical history information or surgical history information or genetic information or signals from their monitors on the wall. And I'm just saying, these are my patient IDs. The computer has no idea what features to look at, right? There's no sense of anything beyond just the information that you have given it. And this is one of the key things about AI. And this is why I think all of you are critical pieces of building out the AI in healthcare field. If you just feed in every bit of information, there's a saying in AI, garbage in, garbage out. The more pieces of information that we're putting in without thinking about it, the more the computer doesn't know what to focus on. And this is one of the areas where, again, as clinicians, many of you have some insight into what are the key features to be thinking about, for instance, when you're looking at a septic patient versus a non-septic patient. We were talking earlier about EKGs, right? So many of you, if you're interested in cardiology, you can read an EKG, you know what features to look at. How big is the ST elevation, for instance, or what is the the QRS complex look like, and how big are certain other components of those waves. All of those are features that we can now feed in, or at least have the algorithm learn, this is what I want you to focus on, this is what I want you to think about. And with a lot more of these complex systems now, we can feed in the entire EKG signal and actually tell it to tell me which part of the signal is important. But I'm still giving it a very specific EKG signal, right? I'm not just throwing the entire medical record at it. And so this is one of the areas, again, that as clinicians, a lot of you will start need to think about, what is it that I want? What is the question that I'm trying to answer? And what are the features that are going to be important to feed into the AI systems? And ultimately, what is it that I want to achieve? So that's classification, where I can break up my entire group or my population into two different groups, or three different, multiple different groups. And I'll go through a couple examples of questions in a little bit. There's this other group of machine learning that can also be applied to what's known as regression. And so classification is if I'm feeding it into a categorical variable, meaning these are, either they become septic or they do not become septic. That's a classification problem. Regression problem is more like, what is their A1C level going to be after 1 year? So it's a continuous variable here. It's a numerical value, not a categorical value. And so both supervised machine learning can achieve both of these depending on how you set up the program. But what I want you to know is, again, this is what these machine learning algorithms can do. And so when you're reading a paper about AI, or you're talking to someone about AI, and you're thinking about what the question is that you're asking, I want you to be thinking about, is it a classification problem? Again, are they in this group or that group? Or is it a regression problem where I'm trying to get a numerical value out from this? Now, you can make the argument that sometimes regression problems and classification problems are very similar, right? So if someone has a high A1C value, for instance, they're likely to be diabetic. And so diabetes is a classification problem, A1C is a regression problem. It really, again, depends on what is it that you're trying to have the AI system find out for you. All right, so let me go through just a couple of examples and these are all research problems that I'm currently working on. So first off, there's a project that I'm working on right now where in the primary care setting, we want to understand if a patient, this is an elderly patient that comes in, if they have mild cognitive impairment, or has their brain started to deteriorate. Many of you have probably heard of some kind of story or something where, someone's grandma was doing completely fine, and then suddenly something happened, and then now they're not thinking properly anymore. They're not oriented well. They don't know where they are. They were found lost wandering out in the streets. Mild cognitive impairment is an understanding in the neuropsychiatry world that there is a space in between where someone may not have fully lost their cognitive faculties, but they're starting to drift towards that. And what we're doing in this particular study is we built an app that a primary care outpatient physician could use. And all it would require is for the patient to say a few things, to talk about a favorite memory, for instance. And it will just record their voice. And we are extracting features from that voice and then feeding it into an AI system. And so as an example, what's been known about mild cognitive impairment specifically is for a lot of people where they're starting to lose their cognitive ability, they're starting to decline a little bit, they'll have some trouble finding the right words to say. And so their speech will start slowing down a little bit. There's also some studies that have shown that their speech patterns become a little bit more flat. They're not as expressive. They're not going to have these, really energetic voices and then some really quiet portions of their voice. It's just going to be a lot more flat and a lot more monotone. And so we're able to start picking up some of those features. We know that the amount of words they'll start using is going to start being different. They'll use the same word over and over again a little bit more frequently, and we can start calculating some of those ratios. And so by extracting those features from someone's speech patterns just through a simple app, we can now tell the physician, hey, this is someone that we think the probability of them becoming mild cognitively impaired is a little bit higher. They should get screened by a neuropsychiatrist. So the app isn't making a diagnosis necessarily. It's helping us screen who should be seen, who should be followed up for further review by a human physician. This is another study that I'm working on right now. How do we determine if a patient is of high risk of falling? And again, this is the same idea. Many, smartwatch technology, smartphone technology is pretty prevalent now. Many of us have a smartwatch or a smartphone. These are becoming relatively cheap as well now. And so one of the things we've been thinking about is, would it be beneficial for us to actually give some of these watches, for instance, to some of our older patients? And so as they're walking around, from the watch, we can calculate how fast the watch is moving, how much the watch sways as they're walking around, right? We can start measuring some things about, are they moving from side to side a little bit more? Just from the watch and the smartphone that's in their pocket, we can start calculating a lot of these features and identifying if the features from one day look a little bit different from the day before. And so a lot of this particular project, the goal is, how do we reduce the risk of falling as opposed to simply detect when the patient has fallen? So for instance, Apple Watch has developed fall detection, right? And so if you fall down, Apple Watch will send an alert, and that's great, and we need that kind of technology. But in our minds, even better is if they don't fall to begin with, right? Because once grandpa and grandma falls down, their hip breaks, something happens, they end up in the hospital. And at least from a lot of the research, once they're in the hospital, they don't always come back out the same. And so again, this is one of those areas that when we're thinking about what is it that we can capture, what is it that we can collect from these particular patients, how do we use some of this new technology that's available to us now that wasn't there before, and use those as features for our AI systems to build these prediction algorithms? How do we determine if it will become septic? We mentioned this already. And so right now we are feeding information like heart rate, respiratory rate, blood pressure monitoring. All of that's is getting fed into an AI system right now to learn how do we determine which patients will become septic and which ones will not. And again, so all of these are classification problems. Now these are very similar questions, but kind of framed a different way, where these become now regression problems. So how do we calculate a fall risk score for an elderly patient? How do we quantify a subject's cognitive workload? And how can we determine how long ago a patient had a stroke? This last one is kind of interesting because, as you all know, if someone's coming in with a stroke, you can give TPA or clot-busting medication, but only within a certain window of time. If you give it too late, they're at risk of bleeding out in their brain. But many times we have patients that come into the hospital where we don't know when their last known well was. They might have gone to bed and then woke up feeling a little bit off. Maybe they were doing something, and then again, they don't remember when the initial insult happened. And so because of that, it's become a very hard thing to know, do we give this person medication or do we not? How do we know if we can treat this person? And so this particular study, what we've been doing is we've been taking the imaging studies. When we get a CT scan, for instance, of the particular individual, we'll take the CT scan, we'll take some other demographic information, how old they are, how much, what kind of medical history they have, and we'll feed that into an AI system. And we're trying to estimate how long ago their last known well was. And so this is one of the problems that we're working on right now, to try to see how do we improve neurological care from this perspective as well. So again, these are all the different kinds of questions that we could ask, framed in terms of whether it's categorical or continuous outcome. But all of these, as you can see, we're always asking the question, what information am I using, and how am I using that? What am I using that to predict or anticipate or classify? So hopefully by now, that's kind of helped you understand a little bit about what AI is doing. One of the things that I'm always a little bit cautious about is, I think too many times, especially in the media, it's very hyped up that AI is this magical black box that we just throw information into and magic comes out. And I know some people do think that way. I was talking to another professor that was like, well, why don't we just hook up the entire medical record system into our future AI systems, and it'll just tell you what every patient has, what their problems are, and it'll just diagnose everything, right? And then there are people that sometimes think, well, we can just replace doctors with AI systems, and that'll be kind of the future of medicine. For me, I think I'm a little bit more conservative with a lot of this, and I think the best thing for us to do actually is have AI partner with human doctors. I think it's this collaboration between how do we as humans work with AI systems, and how do AI systems provide some of the stuff that we're not able to do well. And this then kind of builds a much better system, I think, than if we assume that AI can solve all of these things magically, or predict the future in many ways. Many of these AI systems, and we'll talk about this later, but when we're talking about how well these AI systems work, how do we understand the accuracy of this? We start thinking, at least for us as clinicians, we're thinking about this in terms of how sensitive is the AI system, how specific is the AI system, right? We might talk about positive predictive values. Just a running kind of joke that we have in our lab is most of the papers that you'll look at, they'll say that the accuracy is around 0.8 to 0.85, maybe somewhere between 0.7 and 0.8. So it's accurate about 80% of the time, which again, like all of those concerns that were raised about mycin years ago are still present, right? Like, what do we do with a system that is right 80% of the time? Who's going to be legally responsible for the other 20% of the time? How do we understand, what do we make of, well, who's it right for and who's it wrong for? And if we treat AI as just this magical black box system without any understanding of what's going on inside of it, then it's very hard for us as clinicians to use. It's very hard to get it adopted into these systems. And so this is where, again, if we can build AI system that explains well, how do I take this set of inputs and estimate this sort of outputs and give you some insight into what's going on, then I think that actually helps clinicians be able to move past some of the basic things, the grunt work, for instance, that is required in order to come up with potentially new insights into how the body works and how do we treat and care for our patients. So let me just kind of talk a little bit about how do I use it. And this is the framework that I have kind of showed a lot of my students and have them kind of think through. So first off, and this is true for any research question, this is not just an AI thing. What is the question that we're trying to answer? And so I gave you a list of questions before, but oftentimes I think we might think about AI as this is some grand nebulous idea. We're just saying we want to solve cancer. And that's a very grand question, but not something that we can test, not something that we can actually analyze. So what is the question? So let's say the question is to predict whether or not a patient becomes septic in the hospital. And so these are the four components of any AI system. And again, I'm going to walk through each of these. My goal for today is to really help focus on those first three. Perhaps in a future lecture, we can talk about the technical details with regards to algorithms. But I think as clinicians, it's important for us to understand what is the data we're using, what are the features that we're extracting from the data, and how are we labeling our data? And I'll talk about what that means in a little bit. So let's first talk off. So the question is, will this patient become septic? Well, what are the right things that we want to consider, right? And so our data, for me, as I mentioned before, I'm a signals guy. So I like looking at signals in the hospital. I like looking at EKG, respiratory signals, body temperature, all of those things. When we're looking at, say, for instance, heart rate, what are we doing with that data? And so, at least in the NICU, what we have started doing is we started looking at how many bradycardic events have happened. How often does the patient become apneic? So how often does their heart rate start slowing down? How often do they stop breathing for 20, 30 seconds at a time? And we use that information then to try to predict, does the patient become septic? And even the question of septic is an interesting one. As I've been talking to my neonatology friends, when do we determine when someone becomes septic? Is it when the blood culture is done? Is it when the clinician thinks we need to do the blood culture because they start seeing signs that there's something going on? And again, this is part of the discussion that clinicians and engineers have to work through. Well, what exactly are we defining as our outcome? What is it that we're trying to predict? And so for us, at least in this particular problem, we determined that it's when the cultures are being collected, because then we know at that moment, if there's bacterial growth on the culture, we know that they are indeed septic at that particular point. But again, these are conversations that we need to have so that clinicians can understand, well, if my algorithm is predicting that the patient is becoming septic or is septic, well, what does that mean? Well, it means that it's very similar to all these other patients that we've seen that have had a positive blood culture drawn at that particular moment in time. And then so from here, this is where, in many ways, the engineers will then take and choose their favorite algorithms to then apply to this particular problem, right? But this part is actually, in many ways, the smallest part of the AI system. If you don't define your features properly, if you don't define your labels properly, none of the AI results are going to mean anything. And so this is one of those things that I can get. I work with a lot of undergraduate and graduate students that are starting to do machine learning now, and almost any of them can take one of these algorithms and write a very quick program that will do this. What they can't do is they don't know what the data is, they don't know what the features are, they don't know what the labels are, they don't know how to interpret it. And I've seen many engineering students that will just take whatever data you give them, throw it into an algorithm, and spit out some kind of accuracy that we can predict it 80% of the time. And then for an engineering student, they're done. They're happy with that. For clinicians, that doesn't help us all that much, right? If we don't understand how it works, why is it working? If we don't understand what are the outcomes that it's predicting, what are the inputs that are getting fed in, it's not as meaningful, it's not as useful. It doesn't, for example, if the algorithm says the patient is septic, why are they septic? What should we be giving them, right? Those are all the kinds of questions, follow-up questions that a clinician will be thinking about. And this is why feeding in and designing these algorithms or designing the problem properly is something that I think clinicians need to be involved with so that they can then meaningfully apply those results and understandings now to actual patient care. So let me talk a little bit about interpretation here. How do we interpret a lot of this stuff? One of the things that I'll touch upon this a little bit more. It's how am I doing on time? Okay. So I'm going to cover some of the technical kind of terms that we use in the AI system about how do we understand how do we interpret a lot of these AI systems. But what I want to be, again, what I think clinicians need to be thinking about is when they read a paper that talks about using AI systems. I don't know how many of you may have seen papers that are like, hey, this AI system now is able to diagnose X, Y, and Z better than clinicians or better than doctors. Have you guys ever seen those papers or heard of those papers? Maybe news articles that have come out that there was one that was recently saying that, AI can look at X-ray scans or CT scans and diagnose cancer much better than radiologists can. One of the things that is important, I think, as clinicians is to not just simply take those headline statements at face value and actually think through what exactly happened, right? What data was actually used to build those AI systems? What population was being used? These are all, in many ways, these are all basic research questions. And what I want you to get comfortable with is just because it's an AI technology or tool that's being used doesn't mean that all the basic fundamental research practices go out the window. So let me give you another really good example. A few years ago, there was an app that could take a picture of a mole on the skin, right? And this was a big thing in the dermatology world. We can take a picture of something and then it'll automatically tell whether this is a benign, mole or do you need to go get that checked? Is it malignant or not? And again, the papers came out and it was like, this is really accurate. It's outperforming dermatologists everywhere. What was found out later, actually, this was by one of my colleagues at UT, is that the entire data set was only used on people with fair skin. So if people have very light skin, that's what the data was trained on. And as you can imagine, I don't know if you've seen it in textbooks, but many times if you have these very clean pictures of what a mole looks like, what a malignant tumor looks like or a skin lesion looks like. It's usually like draped with blue towels around it. It's very clean. You can see the skin very well. You see the mole very clearly. And it's usually a fair-skinned person just because it helps you see the edges of the mole a lot clearer. The entire algorithm was trained on thousands of images of these particular moles. What my colleague found out is that this algorithm worked really badly on anyone with dark skin, which logically, when you're thinking about it now, makes sense. If the data is only trained on fair-skinned people, how would the algorithm know what to look for in dark-skinned people, or where the edges are, or how well does it determine where those boundaries are now, right? We have that's outside of the scope of the data set that we were using. And so this is, again, this is a research, this is a basic kind of research ways of thinking about it. Whenever we're looking at these papers that say, well, this is the new medication to give, or this is the new treatment to give, for instance, or AI does a better job diagnosing this population. As clinicians, many times we do have to ask ourselves, does my patient fit in that population? Is my patient represented in the population that the study was done in? Just as another example, and this one's not AI related, but hypertension is a big issue in America, high blood pressure. And we have very strict rules about what medication you give and what's the protocol for what medications to try over time. If that first medication doesn't work, then you give a second medication, or then you switch medications. Again, this is a study that was done recently that showed that almost everyone that was in that original study that determined that those national guidelines were, for the most part, middle-aged white people. And so how well do those protocols work now for the African-American population, the Asian American population? That became a really open question that the national level had to start rethinking about. We need to kind of redo some of these studies with a much more generalizable audience so that we know our results are generalizable across different populations. How is the data being labeled? I talked about this a little bit earlier with regards to sepsis, right? Something as simple as sepsis, we can all say, well, I want to know if the patient's septic or not, but what exactly does that mean? And depending on where we define that, we might get different results. We might find different things. And so this is, again, one of those things where engineers are not going to know about. How do I think about this? How do I label my data? And then what is the specific question being asked? Many times, because we don't know what the underlying health state of a person is, we use other metrics. We use other things as surrogates or as replacements for the thing we actually want to measure. There was a study done a while ago. Now, this is not at the patient care level, but at the kind of hospital-wide level. They were trying to figure out, if we have a limited resource of this particular medication, who do we give it to? And what they did was they looked at all of their historical data sets, looked at all of the patients that did well, that were able to leave the hospital quickly with the medication versus those that had to stay in the hospital for a lot longer. And they used that as their data. And they labeled how fast patients were leaving the hospital as their marker of how well a patient was doing. Now, and so in doing that, what they found out afterwards, after they found an AI system, they built the AI system, they found out afterwards that the medications were going more towards certain races, certain people in the population versus others. And often the people that were doing well would be the people that had a lot more money. These were the people that could leave the hospital because they had facilities to go to, they had the money to pay for nursing care. The people that didn't have those resources would have to stay in the hospital longer because they didn't have the outside resources to take care of them. And so that simple proxy that was used then now shifts the entire healthcare system towards giving treatment just to people that are more well off, right? And so again, this is one of the things that as doctors, we have to be cautious about when we're thinking about the entire person, about who is it that we're caring for, what is it that we're asking, what is it that we're labeling, and what is the population of the data set that we're using. And so again, this is one of those things that we can talk more about in a future discussion. But what I wanted to just really briefly touch on just in the remaining few minutes is many of you may have heard of deep learning, and this is now, in many ways, it's a much more bigger computer system of supervised machine learning. It's a much it can start finding interactions and relationships to build much more complex models because a lot more computing power is put into it. So I don't know if you're familiar with, but a few years ago, DeepMind, an AI company, built a computer system that could beat the worldwide champion at Go. Chess had been beaten a long time ago, and for the most part, chess, you could build a rule-based system. There's enough kind of permutations that you can set up fairly strong chess programs. But people thought Go was going to be something that could not be beat for a long time. And with deep learning, which what it does is essentially adds a lot more computational power. It's a lot more complex. It can learn. The model is a lot more deeper. It learned how to be able to outperform human players much faster than anticipated. Again, I can talk more about the technical details about that later, but just wanted to put that on there, that deep learning is a technical term that refers to how complex these models can become. Large language models, this is what ChatGPT is. And as was said, in the last couple of years, we've seen this explosion of ChatGPT. Some of you may have used Microsoft Copilot or Google Gemini. All of these things where you can start, talking with these algorithms. This is under this large language models framework. It overlaps a lot of what you see here. And I don't have enough time to talk about it today. And again, we might do this in a future lecture. But one of the things that I want you to be aware of is that large language models are in many ways a prediction algorithm. It's treating words as numbers and then trying to estimate what is the next best word that goes in this sentence. And so that's how it's able to make sentences fairly clear. I realize this is a little bit small, but let me just tell you what's going on here. This was a while ago. All of the LLMs now have kind of fixed this problem. But a few months ago, you could ask ChatGPT how many R's are in the word strawberry. Now, most of us, when we're thinking about strawberry, like we can ask someone that's learned the basics of the alphabet, and they can look at the word and they can count how many times the letter R shows up in the word strawberry, right? And so there's one in straw and then two in berry. Almost all of the algorithms, whether it was ChatGPT, Microsoft, Google, all of them said two R's in the word strawberry. And as you can see here, it was very sure. It said there's only one in straw and one in berry. And what I want you to what this illustrates is that these large language models don't actually understand the logic of what you're asking. It's taking the words that you've constructed and feeding it and transforming it into a mathematical it's transforming it into a mathematical space and then using it to generate probabilistic answers of what would be appropriate to respond to your particular question or thing that you're saying. And because it's learning from everything that's ever been written, it's learning from a lot of languages, it can sound very human-like. It does a really good job of explaining a lot of things, of saying a lot of things, because it's pulling from everything that's ever been written. So if you're asking stuff where you want to understand concepts, ChatGPT is pretty good, or any of these algorithms are really good at kind of pulling. In many ways, you can treat it as a really powerful Google search, right? It can pull all the information and generate realistic sounding words. But because it's a probabilistic model, it can also start making up stuff. And so, for instance, I've asked to find a paper for me before. If I asked it a research question and say, can you give me a reference for this? Can you tell me who's written about this particular thing? It's made up a reference for me before. And when I said, I can't find this in the journal, and I can't see this in Journal Nature or in Science or Cell or any of these other big journals, I can't find this reference that you've told me. It says, oh, I'm sorry, here's another reference. And then it just added a few more names to the authors list. And so this is what's known as hallucination in a lot of these large language models. And so this is why, while I use ChatGPT quite a bit, or Copilot, or I have these conversations a lot of times, these things are really good at helping us by working alongside of us. They're not good to replace us. And so this is one of the things that, again, we can talk more about this later in a future lecture, but I wanted to at least put this out there that there are some really good tools if you want to learn some information. But one of the things that I found is you always have to kind of check those information points with other sources that you know are reputable. Finding the original paper, for instance, that they supposedly cite, reading that paper, understanding those different things. So in no way am I saying don't use ChatGPT or don't use large language models, but just be aware of, this is why I think, again, it is important for students, for clinicians to be aware of what is it that they're using and what are some of the limitations. What is it, where is it good and where is it not yet capable of doing some things. So I'm gonna end it here. I'm gonna just open up the floor if there are any questions or anything. But let's, yeah. So we'll are there any questions?
Why can't it count 3 Rs?
Why can't it count 3 Rs? So again, like I said, strawberry is what ChatGPT does is converts it to a string of numbers. And so those string of numbers have no meaning. It has no meaning. It has no knowledge that strawberry is spelled Strawberry. It just has a concept of strawberry in its database. And so even now, I think when you ask it how many R's there are, that concept, this question has come up so many times on like the forums online that ChatGPT has learned from the forums that the right answer is 3. But it doesn't process it. It's not processing that. This is how you break down this word. This is what this word means.
That's going to be like future like improve learning, or you think it's just gonna be
I think that people are, at least for this problem, people are realizing now that, again, one of the basic things about strawberry is as a set of numbers. And so they program that into the internal model. So something like this, I think, I think there won't be an issue here specifically because they're now teaching ChatGPT this rule. And so this is a really interesting place where actually human rule-based intelligence essentially is kind of working alongside of machine learning intelligence, combining some of these things together. Yes.
What database that is like diverse? Will it be like diverse? Because like maybe like information like race inside has a black race, and then another patient is it might be male, and if we like kind of have a database that is like risk diagnosis.
Yeah. So so the question is, if you have a very diverse data set, is that a risk of potentially having really bad correlation values, right? Because now you're trying to correlate, black, whites, Asian, all of these different races all together. And what I would say is that as long as we're very clear about race being an important thing, then we specify that this is now a feature that we want our algorithm to pay attention to, right? And so that's when we say, okay, this is one thing to keep in mind, then it should hopefully learn and build a model with race as one of its input features. But you're right, if we simply throw everyone together and we don't tell the AI system that race is in there and now we mix everything up, then it's going to have a really hard time figuring out, well, what's the right diagnosis, because it's just going to come up with a very generalized model for everyone, which is not going to be specific for anyone.
So like the important bit is like categorizing the data before you like kind of start the machine learning, then that's the process, right?
Yeah, and this is one of those things where I said, you as clinicians, you'll know, or you have a better sense of what is the important thing and what is not important. And so, if race is going to be an important thing because we've seen other studies talking about race, for instance, then we need to make sure race is part of our feature set.
Another question about like the AI. I know that there's a lot of development in like big cities and developed countries. How can we apply that to like localize to some like in rural areas or like developing countries? They barely have access to these technologies. Can we still like help them out in terms of AI uses?
Yeah, so I think that's a really interesting question. One thing I will say is there's a lot of AI technology that is becoming a lot more accessible today. Where if you have someone that can do a little bit of programming, for instance, we can deploy and set up a classifying system or a supervised machine learning system. One of the biggest things that's missing right now from a lot of the big companies, like for instance, Google, Apple, part of the reason why they haven't yet quote unquote solved AI medicines, they need to work with a lot of doctors to get the actual data itself. And so I would say even in developing countries, especially if you want to build an AI system that's specific to that particular population, you need data specific to that population. And so this is where I do think a lot of partnerships between clinicians who are at least aware and understand the big picture of AI from some of those places. If we can do more education with regards to what AI is and provide, again, like I said, I think the engineering piece of it, some of these problems do not require very complex engineering or programming to build a simple supervised machine learning algorithm. A lot of it comes down to knowing what your data looks like and being able to process a lot of that. So I think a lot of it in the future will come down to really good partnerships between countries that have those resources and countries that don't have those resources.
I think, yeah, that answers my question. Thank you.
All right, thank you.
I'm going to be asking two main questions. So the first question, I would like your perspective on the black box problem and how potential solutions could be implemented that are better than what we have today, or like the logical reasoning of our generative models.
Yeah, so the black box, sorry, were you going to ask the second question too, or?
I'm going to go one by one to know.
Okay. So the black box problem is one that a lot of the computer science people are well aware of, and they're working on right now. There is a number of techniques right now that are being used to try to take the results from the black box and kind of bring it backwards through the AI system to understand, well, what is it about all of these features that led to this conclusion? So I saw this really cool illustration of this recently with these image recognition algorithms. And so, for instance, if you look at a picture and it's trying to identify cat versus dog, which is a very classic image processing question in the AI world, the algorithm, the explainable algorithm essentially will tell it which pixels are the key important pieces that help it define cats versus dogs. And so in some instances, you'll see a really cool outline around, like, say, for instance, the ears of the cat. And that's how the algorithm has now determined this is a cat versus a dog. And so this is one of those things that, one of the ways that I think people are starting to develop and build tools to do a little bit more explainability, so that, again, we're not just saying this person is septic or not septic, but we're saying why this person is septic or why we think this person is not septic.
Okay, thank you. And for the second part of my question, it's a bit more about image classification algorithms. Specifically, I'm talking about those that you can use to classify metastatic in cancer, especially in lung X-rays. Would you think that custom trained algorithms or algorithms based on general classification algorithm layers could a specific learning data on top would be a better option, general and in specific use cases, such as the classification of lung cancer stages?
Yeah, so no, that's a really good question. One of the things in medicine, at least, right, when they trained cats versus dogs, for instance, they trained on millions of images, and we don't have access to the same millions of images for all the different classifications of lung metastasis or lung cancer. One of the things that has been done and developed in the AI world is how do we train it on some basic image processing first, and then have it now fine-tuned on our specific use case. And one thing that I kind of use as an example is, if you've ever seen, like, if you think about how we learn how to recognize things, right? As young kids, we learn very early to distinguish shapes and colors. And then from those shapes and colors, we build out images. Like, our understanding of what do we see then gets fed through those initial layers in our visual cortex that starts putting things together until now we're able to see complex objects and understand it, and with that foundation, right? And so in many ways, the computer science people have started to try to use a lot of those similar processes by saying, if we have a very deep layer of neural networks, for instance, can we simply retrain the last few layers or retrain part of the model on just the data that's specific to our use case? So for instance, lung cancer imaging or lung imaging. And then that way we don't need to retrain it from the ground up. And so you're absolutely right that there is a lot of work being done right now into what you're describing, where how do we leverage what's already been learned without having to kind of recreate the wheel all the way from the beginning.
And does anyone have any more questions? Because I have one more long question there.
Yeah, sorry. It's a bit off topic, but I was curious about because I know that one of the biggest reasons as to why there's apprehension towards using AI is the environmental impact that AI has. And I was just sort of curious if there's been steps towards minimizing or decreasing the amount of environmental impact from like AI usage, especially since like in recent times the large scale AI usages create a lot of wasted energy and things.
Yeah, no, that's a really good question. I don't know as much about that side of things. The couple of things I do know is, for instance, as you said, there's huge amounts of processing and compute power that's required for a lot of these models, or at least to train these models. Once they've been trained now, then the actual model itself is relatively lightweight. And so now, that being said, though, once you have that model, though, it's not learning anymore. So that's where some of the challenges are. So I do know that there's research being done right now to try to understand how do we build these learning systems with this base model that we've already trained. We've already used all that energy. But in moving forward, how do we minimize that energy consumption a little bit more? So I do know that that area of research is ongoing. The other thing that I'm also aware of is I think people have started using AI as well in the computing centers themselves to know how to optimize airflow, energy balance, and all these things to minimize electrical energy use. How well, by how much, I don't know for sure, but I do know that it's one of the problems that they are working with.
Thank you.
So you talked about the large language models of the AI. So I'm not sure if you have gone over how these large models handle the contradiction or the ambiguity in the language itself. Like how does it handle that? Or is it just purely a pattern recognition and like doing like puzzling, doing something like matching puzzles?
Can you give me an example of the contradiction?
Like, sorry, I couldn't think of one on top of my head right now, but like sometimes you have sentences or phrases with maybe implicit meanings or like not nothing explicit, something that you have to read between the lines.
Yeah. Okay. Let me give you an example and see if that matches what you're doing. So two things come to my mind. One is very early in my AI training, I came across our professor gave us this phrase of Saudi head seeks arms. All right. And you can interpret that as if Saudi head of state, like the president or something, was looking for weapons. Or if you were very cartoony, you could imagine it as literally a head looking for its arms. Right, depending on the context that you're looking at, whether maybe it's a video, right? So that simple phrase, is that what you're referring to by potentially implicit or alternative meanings to this?
Yeah.
Okay. So one of the things that, again, the probability models in these LLMs, I think, if it's something that it has seen before, like if the usage of the word head in these different contexts, right? The head as in the part of my body, the head as in the figurative head of the state, if those meanings are in its training data set, then it'll then model that as part of its probabilistic understanding. So I have asked ChatGPT about this particular head-seeking arms, for instance. I was curious what it would say. And depending on the way that you ask the question, it will give you every possibility and kind of ask which one do you need. Now, let's take it a step further, though, because one of the things that we are finding out is because ChatGPT is so optimized to match words to numbers, right? Because again, all these large language models are essentially building their premise around treating every word as a numerical string. treating these concepts as new numbers. If it's a concept that has never seen before, you and I as humans, we may draw the comparisons. There are certain things that maybe have not been written, but we would understand what it means implicitly, like you said. AI would have no knowledge of that and wouldn't be able to generate that. And in many ways, the large language models are so optimized right now that they can't make those extrapolations.
Oh, so as of now, it is still unable to learn without context.
As of right now, it is still learning. But one of the things that my understanding is it's learning the content of everything it's ever learned, right? And so if, for instance, let's just say hypothetically, I used a word in a way that's never been used before in my conversation with ChatGPT, it's not going to propagate that understanding between how I just used that word into the rest of the language until it's more widely used. It's not going to rewrite a lot of its underlying learnings just based off of my conversation and the way I revised one word, for instance. So that is one area that, if we're talking about, and this is something that, at least in the context of medicine, has been a big question. Sometimes we will see a patient that we have never seen before, has not shown up in the literature, has not, this is a really true zebra of a case. AI, as of right now, doesn't know how to handle that. And it doesn't think through the possibilities like a lot of clinicians would with regards to, well, how do I systematically think through the etiology of what's going on? How do I work my way up to figuring out how to solve this problem? ChatGPT or large language models as of right now are still very much, this is the data that I have, this is what's probabilistically going to make the most sense.
Thank you.
Yeah, I just had one question, kind of open-ended, but the kind of AI that you like deal with is mostly about pattern recognition, right? But I was wondering about what you thought about the future, like the potential of like having AI being involved with surgeries. Because like I know that in Highlands Hospital we have like the Da Vinci bot. I'm not sure how much AI is incorporated within that, but I know that it's automated. So I was just wondering your thoughts about how, or maybe even if AI could be used to assist, or if it could have the potential to help in like surgical procedures.
Yeah, that's a really good question. When I was doing my surgical rotation, my surgical attending commented that he wasn't scared about AI coming into medicine because all the different fields, surgery would be the last one that AI would finally truly get hold of. Because of how precise the surgical process was, right? How tactile and hands-on. I do know, as you said, the Da Vinci, and even when we were training, some of these machines were being developed for very precise, very, very tight stitching and so on and so forth. I don't know enough about the Da Vinci's in terms of what exactly it's automating. Is it automating something where it's, you set up the parameters and it's kind of doing the suturing, but it's a very pre-programmed set of sutures that you can set up, for instance. The thing that I am cognizant of right now is with regards to surgeries, like if you have a pretty normal surgical process, everything's working okay, generally it's a pretty simple process, right? I know, for instance, when I'm doing rotation, we would see cholecystectomies like regularly, multiple times a day. So doctors have gotten really good at it. But where the surgeons often, like where the really good surgeons shine is when something unexpected happens. Right? When something you do not intend or do not expect to happen, say an appendix burst or something, how do you quickly recover from that without causing more damage to the patient? And so that's something where I don't know enough about where the robotic world is with regards to AI to know how well it would handle under those particular circumstances. And in many ways, if you think even with robotics, right, and there's a lot of AI with robotics out there, at the end of the day, it's still similar things. You're defining features a certain way. You're defining features in terms of the acceleration of this robotic arm in this direction versus the movement in this other direction. And so driving cars, for instance, right, is a lot of AI. It's recognizing what's on the road. What do I do? Again, it's defining what your inputs are, what the labels are, and how you're setting it up. I think it's the same underlying principles, but the actual application itself. I haven't read enough about the issue or where the surgery is right now.
Thank you.
Thank you very much.
Thank you so much for the question, and thank you so much for being here in coverage. Joshua Chang. As you said, he will be helping us with a little bit of lecture later on for some of the IP, maybe a little bit of weekly courses for future AIs and medicine. So thank you so much everyone for coming here. And if there's any more questions, you can send it to me and I'll have to mark George here. Thank you.
How many, like, you think in the other medical school around the United States, are they giving so much emphasis onto this in computation or in AI stuff? Like amongst your, that you know?
We're trying to do it at UT right now. But it's been really hard to get anything going.
Why?
I think part of it is everyone's got their own opinions of how it should be and what should be focused on. So I come at it much more from a technical perspective. Other people are coming at it more from just how do I use ChatGPT better?